So now we're talking about the very fascinating topic of significant figures. Try to contain your excitement, everybody. I know a lot of people roll their eyes about significant figures. Maybe you don't get why it's important, but it's actually really, really important, especially in experimental science and engineering. The concept of significant figures makes a huge difference. And I'll talk more about that in just a minute. But first of all, let's talk about how significant figures are going to come into play mathematically. It's primarily going to be when you're multiplying or dividing. So this is about how do you decide how many decimal points to write, essentially, in your final answer if you're doing a calculation. And in sciences, you make that judgment based on the number of significant figures in the numbers that you're working with. You have to know how to count how many significant figures does a number have. And if you're doing a calculation with two or more numbers, your final answer should have the same number of significant figures as the least precise number going into the calculation. So the limitation is, what is your vaguest number, basically? The vaguest number involved in your calculation tells you how vague your answer should be. So let's go over the rules and then look at some examples. So what is a significant figure? Anything that's not zero is significant, so that's easy. And zeros are significant if they're in between two other numbers which are not zero. And the other time that zeros can be significant is if they're all the way at the right-hand side of a decimal quantity. Essentially, if you have zeros on the end of a number that has a decimal in it, those zeros are usually going to be significant. So let's take a look at a few examples, shall we? 5.2. Clearly this number has two significant figures, right? They're both two numbers and neither of them are zero. 5.02. This number has three significant figures because we have the 5 and the 2 and then we have a 0 in between. So 1, 2, 3 sig figs. This third example is getting at the last point from the previous slide, zeros which are at the end of decimal numbers. So here we have the 5, and then we have the decimal, and then we have a 2 and a 0 at the end. So anytime you have a 0 at the end of a decimal number, that is significant, and I'll talk more about that in the next slide. But because this is a 0 at the end of a decimal number, it is significant. So 5.20 has three significant figures. To contrast that, this next number, 520,000, only two significant figures because we have zeros on the right-hand side, but there's no decimal. So all of these zeros are irrelevant as far as significant figures are concerned. And another way to think about that is we could rewrite this number using scientific notation. 520,000, it's the same thing as 5.2 times 10 to the fifth. Scientific notation and significant figures work really well together to help you streamline your calculations. So another example of a number which looks big but which has very few significant figures would be 0.00052. We can also rewrite this using scientific notation, 5.2 times 10 to the minus fourth power. So all of these zeros on the left-hand side, they are not significant. If I had something else over here, like a 1 or any number, obviously, then all the zeros would become significant. But because it's just all zeros, none of them are significant. So why is this zero significant, whereas these are not? Well, it has to do with the connection between significant figures and measuring devices and tools. When you write a number with decimals and then additional information after it, every digit that you write down is a way of conveying how accurate, how precise is your measurement. For instance, if I have a scale and I'm measuring the mass of something, if that scale says 5.2, that means I know that the object weighs 5.2 grams. It might weigh 5.23, and the scale is going to round to 5.2. It might weigh 5.18, and the scale is going to round to 5.2. So if your scale is only showing the 0.1 digit, then there's some rounding happening, and you don't really know exactly how much that object weighs. It's somewhere between 5.24 and 5.16, and your scale is just doing the rounding for you. But if I write 5.20, let's say I take the same object and I weigh it using a more accurate scale that gives me more information. If that scale says 5.20, that means it's telling me all the way down to 1/100th of a gram, this thing definitely weighs exactly 5.20 grams. So it's giving you a higher degree of information. And if you write down a 0 after a decimal point, that is you telling another scientist who's reading your work, I have accurately measured whatever number it is using this level of precision. So the zeros, the number of zeros that you write is actually very serious business. If you can imagine being an engineer for a space agency or building advanced technology where the level of precision is really important, and so you have to be really clear about how precise your measurements are, and you convey that with how many decimal points you're writing down, essentially. And that's why you have to pay attention to significant figures in calculations. So here's some example calculations. Let's take something which appears to be the same number. If you haven't thought about significant figures, you would look at 5.2 and 5.20 and 5.200 and say, well, that's the same number, right? Because 0 is just 0. It doesn't change anything. But in physics or in other sciences, writing down 5.2 versus 5.20 versus 5.200 means I have a much, much more accurate measuring device down here versus up here. And that's why I'm doing different amounts of rounding in my final answer. Right? If I have 5.2, that means I'm actually somewhere between 5.24 and 5.16. So if we pop open a calculator and we do 5.2 times 5.2, your calculator will tell you it's 27.04. But we don't actually know that our original measurement is 5.2 because there might have been some kind of rounding going on, right? If the number was actually 5.16, for instance, then my answer might not be 27.04, it might be 26.6. If my number was actually 5.24, then my answer could be 27.45. So you see, because the scale is doing some amount of rounding, you don't really know exactly whether your answer is 27 or not, and it could make a pretty big difference. It could be 27.04, but it could be 27.3. It could be 26.8. And because we can't guarantee for sure how accurate our answer is, we only use the same number of significant figures as the least accurate number in our answer. In this case, both of the numbers have 2 significant figures, so my final answer will have 2 significant figures. So 5.2 times 5.2 is 27. If I add another significant figure, now I can have 3 significant figures in my final answer. 3 sig figs here, 3 sig figs here, which means my final answer is now 27.0. If I wanted to see for sure that the answer was 27.04, I would have to be multiplying 5.200 and 5.200. Each one of these numbers has 4 sig figs, so my final answer can also have 4 sig figs.